And then we have to read the instruments in the class.
Oh, I know.
What is Simon gonna make you do?
He's gonna probably put it in like the hundredth place, like the thousandth place on the rod.
Did you like surveying? I didn't like it.
I'm not a fan of it.
I had to redo it like 4 times.
Yeah, me too.
Yeah.
More like five.
Because Simon aggravated me. It wasn't even really him that convinced me to go into it. It was Dawson who convinced me to go into engineering.
Wouldn't his class convince me to like not move on, like to stop at my associate's degree?
He just convinced me more, just straight further.
I took statics alongside the structural drafting course. And I think just seeing the two and how they related was like really important for me, because like I would go to his office and I'd be like, obviously we're not building with triangles and circles, so what is this? So he would show me, this is a shear connection. You know, it transmits shear forces, vertical and lateral, and he would be like, and as you can see here, it's like, of course you wouldn't think like the connection rotates, but it's relatively flexible compared to something that's like like plates welded up on the top and bottom of a beam and then restricting rotation entirely. Or like a concrete beam, for example, cast into the walls. That's like a moment connection.
I didn't even teach structural yet.
You didn't?
Last
Doing that
semester.
next semester.
Maybe I didn't know. I would have taken it.
Is that like, oh yeah, they did change it. Well, I guess, maybe I,
Yeah, you take it whenever you want.
I don't know. I guess. Because I took, during my second semester, I took structural drafting, residential drafting. They don't have advanced CAD anymore.
What's that?
It used to be this CAD drafting. What?
There's a drafting certificate class.
What is it for?
Certificate for drafting.
That's the same class.
Yeah, you get that. You just upgrade when you graduate this degree program. You get both.
Yeah, it's like the drafting course that I'm talking about, the advanced CAD.
But we get both.
Yeah, because all of these we satisfy all the requisites.
No one told me that when I applied for the major.
Yeah.
So I don't know.
But you guys don't have like the advanced CAD course where like you guys are dealing with like viewports in your drafting model at all?
We did that in residential.
You did?
Yeah.
Dealing with title blocks. What about like just CAD blocks in general and learning how to create them, learning
was
how to
residential,
change
too.
views? All right, so I think that they may have just combined the two courses, because like when I took it, we learned a ton of like different commands and 3D modeling too in AutoCAD.
Oh, we don't do 3D modeling in AutoCAD. We do it in Revit.
Yeah, in AutoCAD you do it too, but
I did a little bit of it when I took the intro class.
And then
Is that used commonly in the industry, or is it used
AutoCAD 3D modeling? Not really. There's better software for it. Like for buildings, you would use Revit. For like mechanical engineering, you might use something like Fusion 360. For like if you're doing like site plans, you would use like Civil 3D, which those give you like the really good topography maps, and they're really good for like roadway development.
Are you familiar with like ArcGIS systems? Or
I've heard of
software?
it, but no, I don't have any experience with it.
Because that's what I'm looking to get into, like GIS systems and things like that. But you gotta like get all these certificates.
I'm taking the class on next semester. I'm gonna do a what's it called? Like a mini class on the GIS system.
It's offered here?
It's part of my scholarship.
Oh.
The NSF iSuccess.
Oh, I was part of that too.
Yeah. It's not really for me that much, I'm gonna be honest.
You can get a scholarship here?
Well, I got it originally from
You didn't know you could get scholarships at Suffolk?
There's a ton of scholarships.
Hey, Nicole.
I can get one next semester.
Yeah, just apply. When I was in the program and when I switched to engineering, I got the NSF STEM assets, get there from here, Granger tools, and then I also got a few other minor ones too. Basically, with all of the scholarships I had, it paid for 2 semesters tuition and a new laptop.
Well, my GPA is only a
Thank you so much.
It doesn't matter. All you need to do is be all you need is to be interested in the topics, you know? Like, I mean, with me, I had, I think, like a 3.8 GPA, which, you know, like, I mean, I don't really care about my GPA too much, but what I care more so about was, like, just enjoying stuff, and I think that's why people really, I guess, gave it to me, because I was always so passionate about it. Ask Professor Dawson or Professor Simon. They'll tell you I was already always harassing them somehow. So I think it's just the providers of the scholarship are just looking to see, like, who's the most interested, you know? Because interest and passion really go a long way.
Yeah. I just assumed it'd get
All right. We are still covering the design of beams. Basically, we're just going to be working with shear forces and bending moments. As like a little reminder, your exam is next week. It pertains to everything associated with the design of beams, excluding deflections. Just because with the way that I think these lessons kind of were going, we're kind of behind track on that, but it's all right because I should have expected that just because these are complicated topics. So deflections aren't going to be on this exam, and just for your guys' sake, the deflection homework I initially had scheduled for it due next week, but because, again, I'm not including it on the exam, I pushed it way back after Thanksgiving break, so it's not going to be due for like another 2 weeks. Yeah?
So could you just repeat what's going to be on
Anything associated with beam internal forces and beam design, excluding deflection. So these are your shear forces, your bending moments, shear stresses, bending stresses. Yes?
Are we going to have a review again on Tuesday?
Yes. Yes.
So we don't have any homework this weekend, just studying, or?
Yeah, this is homework 8, which is just the shear and bending stresses. I don't really plan on showing anything new, just because, like, it's not really anything. Yeah, the only thing that I could really add to the exam is deflections, but, like, I mean, I don't want to rush it, so I'd rather just do practice problems, because I know quite a bit of you have been struggling with the concepts of drawing these diagrams out. So, yeah, I just want to focus on that. Yeah.
So what are we doing after this test? Because I think on the syllabus it still says code-based design.
Yeah. So that's all on the Excel spreadsheet. I didn't upload it, but basically the outline for the course after we come back from break, because it's literally just the exam next week and then it's break for a week, right? So after break, we are going to work on deflections and beams. We're going to be working with torsion in circular elements. And then if we get to it, column buckling. And these are all after break, which also are going to make up exam 4. All right? So they're just kind of like miscellaneous topics. Like I said, I wish I could put deflection of beams on the exam because it relates to the stuff that we're doing right now, but I don't want to throw too much on there. So,
Thank you.
yep. Yeah. So, at minimum, it's going to be deflection of beams and torsion, which torsion in itself is, according to Professor Simon, out of all of the years he's been teaching, torsion has been the worst for the students because they don't get it. They don't see that there are rotational forces that are parallel to the cross-section of the elements. And then it's also like introducing something like new with statics where you guys learn some of the moments, some of the forces, but now you also need to know some of the torsions. But it's all the same concept. As long as you understand equilibrium and understand internal forces, you should be good. All right, so let's just get straight into this. Let me grab taking notes. I just want to see what I have covered previously. Yeah, so for columns, let's just, not columns, beams. Let's just start out immediately with another example. All right, this is going to be something similar to what you guys did on the homeworks. And then I'm going to teach like one more thing, like after probably the break, which will be on your exam. But it's not too bad, I promise. All right. This here, actually, I don't want that. What I want is actually that, with a point load here of 25 kips, and it is located 10 feet and 10 feet. Now, this is a statically indeterminate beam. Generally, you would need to know compatibility and do the deflections in order to be able to solve this, just as we did with statically indeterminate bars. However, for beams, I am going to simplify things tenfold and only ever give you guys statically indeterminate beams that will require tables. So you can use the tables to design the statically indeterminate beam. It may be a combination of forces, or it may just be one force like this. It's just a matter of figuring out what the correct value is. But what I want you guys to do is determine the minimum W shape to support the load. I want the shape to be A992 steel, and I want a factor of safety equal to 1.5. All right? So, I'm going to give you guys a few minutes just to determine what the W shape would need to be, and then we'll work it on together and see if the answers you get make sense or if you just killed 1,000 people in a building. Yes.
I just have a question about.
Sure.
So for this, it's like there's a ball in it.
Exactly, it's a fixed end beam.
But then how do I decide if it's negative or positive?
You would need to draw out the diagrams, or you can look at the table, and the table generally tell you.
Okay. So
And if you look at the table, like the design force table, it'll tell you the magnitude and the direction and everything of the forces. Yes.
So if you were going like this, can you just go straight to the table and do M max?
Exactly. So you can figure out what M max would be. All right, so I'll have to upload 2 recordings then, because the first one stopped. How do I gotta like go to my settings and like set the power mode. Power.
Because that was the weirdest thing I've ever heard. You just speak in Spanish and do it last time.
There we go. Guys figure it out? It's a statically indeterminate beam. What did I just say about if I gave you guys a statically indeterminate? Well, yeah. Wrong chart. I remember now, you weren't here when I gave you the table, when I gave out the tables.
I'm like, where? What chart am I supposed to be looking at?
The
Oh, look at that.
yes, so here you go. I'll just print out myself another one, but those include a bunch of shear force and bending moment diagrams for typical cases. Of course, I can give you guys a very complicated load case scenario that won't be in the table, in which case you would still need to know how to draw it, but that just helps with like the design.
I see. This is so helpful. I was doing homework.
Yeah. That should help with like homework 7, I think.
Homework 7, okay.
Homework
That's when
7.
I was like, I was watching the lecture, and I was like, wait, but then, this should help.
Yep.
Thanks.
Yes, Michael.
One more question. Would you be using M design? Would you be using M design or just the regular M max?
Well, the M max is just the maximum. The best way to word it is the maximum unfactored bending moment or maximum unfactored shear force. However, they don't account for any factor of safety. They're just the maximum bending moment just caused from the load without any type of factoring at all. With the factoring now, you take that M max and multiply it by the factor of safety.
Oh, I put two down.
Yeah, so your M design would be your M max times the factor of
I
safety.
think on the homework I did M design just because I was going like based on what we did in class, but I put both in so I didn't just do it. I did it regular. I put a factor safety on there.
Okay. I mean, if you just added a factor of safety, I'm looking more so at your procedure. If
I
you
put
just-
both because I wasn't sure. I was like, if we had a whole
Yeah, if I ever ask you guys to design something, I will ask you guys. I will give you guys explicitly a factor of safety. Otherwise, if there's no factor of safety at all, it is just an analysis problem, and I am just asking you to determine the stresses, just to see if you know how to use the equations.
Alright.
All right, that's still there. I gotta go see if I can't print myself out a new tape.
This is the justice act.
All right, you guys should have this done in about another around 6:35. just want to make sure everyone submits the homework, because I think last class either half the students just chose not to do the homework or just forgot to submit it. Last class you gave up. All right,
But this one,
I'm gonna try. I was just so concerned. I was like, why do I only have 6 homework assignments? Only 4 students handed it in person, and then 2 students submitted it online, which means literally half the class did not submit the homework. Figured out yet? All right. Make it 250 kips. Clearly, I undersized them. So, just whatever your answer is, just multiply it by 10. All right? So just add a 0 after it, whatever your answer is. So with the factor safety, this should just be, instead of it being 25, just make it 250. Your bending moment should be there. The 25 kips for the span seems reasonable. I'm just trying to think. Why would it not be? I gotta print out the diagram just to make sure I'm not like losing my marbles. This is the issue with me making up problems. I gotta just start using tables. Using the textbook. 635. You guys should have a section. Yeah? What'd you get?
W 10 by 19.
10 by 19. Anyone else? You got the same thing? Did you get it in a W shape? No? How about you, Michael?
Oh, I gotta redo it because of the number change.
Just multiply it by 10.
Yeah, that's what I'm doing.
All right. So, I want to hear what you guys did. What did you guys do? What figure did you use?
Figure 16.
You used figure 17. I would have used figure 16. The reason being is because it's located directly at the center, so it would have just made the numbers a little bit easier. But figure 17 would still give you the same answer as long as you did it correctly. So let's go with figure 16. And so for figure 16, the maximum bending moment, M max, is equal to 3PL over 16, which is just going to be 3 times the 250 kips times, what's the length going to be? What is L? 20 feet. Did somebody say 30?
I did not say that. I said clearly, you saw my picture.
And what do we get for the maximum bending moment? I need my calculator. What did you get? 937.5 kip feet. See, now that seems high. But 93.5 kip feet seemed low. I know what happened. All right, I think I know what happened. All right, the reason being is, all right, probably shouldn't have changed the number then, because now I realize this section is going to be massive. So, yeah. Did you multiply the bending moment by 12?
I got that too.
No, you told us at first that it was 25 kips. I know we didn't convert it into inches.
I got that.
That explains why. So, all right. So, ignore what I said about the 250. All right. Michael, don't worry. All right. So, instead of it being 937.5, should be 93.75 kip feet. All right. Now, when you're designing, you got to keep everything in consistent units. So, what you need to do is multiply this by 12 inches per foot so that the feet cancel. What do we get for the bending moment then?
Well, I did that last. So.
All right. I didn't bring my calculator today like an idiot.
42.5.
Oh, wait. Here it is. There we go. It's buried in my bag. So 93.75 times 12 gives us 1,125 kip inches. Now, we also need a design shear force. What is our design shear force going to be? It's going to be either V1 or V2. So, V max, we just look at this, is just going to equal which one? V1 or V2? Anyone? Design shear force. Because you don't only just design for the beam bending. You have to check shear as well.
Is it a V1?
What?
Is it V1?
Nope. It's V2. Because it has the 11, it's 11 over 16, which is greater than 5 over 16. So you would use V2, which would give you 11 over 16 times P, which was the 25 kips. Which is the 17.1875 kips. Now from here, we determine our design forces. So MDES is just going to be our maximum bending moment, the 1,125 kip inches, multiplied by the factor of safety, which we specified was 1.5. So 1125 times 1.5 gives us a design bending moment of 1,687.5 kip inches. Our shear force for design is just going to be the 17.1875 kips times the 1.5 factor of safety, which gives us a design shear force of approximately 25.78 kips. I don't feel like writing out all the decimals, and besides, like, that would be like 1.25 pounds difference. So it doesn't matter at all. All right. Now that we have our design shear force and design bending moment, how do we size out our sections? How do we do it for bending? What's the equation we need to use?
And we can use S equals M over sigma.
Yeah. So you would use the stress equation, which tells us sigma is equal to M over S. But you have to rewrite it to say that S is equal to M over sigma. And so that gives us 1687.5 kip inches. And then what's sigma going to be?
50 KSI.
Why is it 50 KSI?
Because that's the yield strength of A and other.
Exactly. Sigma y is equal to 50 KSI. So we take that 1687.5 divided by 50, and we get a section modulus of 33.75 cubic inches. Where do we go from here? You go to your design tables and you figure out what shape you need to use. I have misplaced it now. Where is this one now? Here it is. You go to your design tables, you figure out what W shape has a section modulus of, at minimum, 33.75. And I already see 1, 2, 3. I see a few. What would you guys use?
W12 by 30.
You would use a W12 by 30? Okay. Anyone else? Any other suggestions?
10 by 33.
You want to use a what?
10
W10 by 33. Okay. All right. Let's work with W10 by 33. Which gives us a section modulus SX of 35 cubic inches, which is greater than the 33.75. So this tells us beam works in bending. Now that we have a shape to work with in bending, what we want to do now is determine how this beam behaves in shear. I said this last class, most beams will generally fail in bending because they're spanning longer lengths, which means that the bending moments are generally larger. The only time that shear is really of concern is when you have relatively small spans. Hence, the general procedure for designing a beam is check bending, or design the beam for bending, and then check its shear capacity. Because usually the bending utilization will be much higher. Make sense? All right, so now we need to check shear for chosen shape. All right, so what did I say about the design for shear in W shapes? if you guys remember, when we had a W shape that looked just like this, there is shear force that develops in the flanges at the top and the bottom, but the shear force is generally very small. So when we design for shear in W shapes, usually we just entirely neglect the flanges and we just take the area of this web here. And hence, when you find the area of the web and calculate the stress for that, we call this the average web shear approach for calculating shear. So we need to use average web shear approach. I am assuming that nobody got to the calculation of the shear stresses. So we'll do that together really quick. So, shear stress in a conventional shape for beams subjected to flexure is usually VQ over IB. However, because of the deviation and the fact that we're making this assumption about the average area in the web, we can approximate this to just say A over the area of the web. That stands. What is the area of the web going to be? What? Nope. Because that's the area of the entire cross section, including the flanges. At that point now, you're overestimating the area of the web. So, the way that you calculate the area of the web is you need to consider the height here. We'll call this dV. This dV is equal to the depth of the overall beam minus the flange thicknesses, which, because you have two flanges, you subtract two flange thicknesses. Does that make sense? And then the area of the web is just going to be that value dV that we calculate multiplied by the thickness of the web, because that's just a square. So the depth D, what is the total depth of the W10 by 33? It's 9.73 inches, right? Do you guys see that? Total depth of the beam. Yeah. So it's that 9.73 inches. And then what is the thickness of the flanges? What do you guys get? 0.435. And so we calculate this, and you get 9.73 minus 2 times 0.435. And the area is the depth is just 8.86 inches. Not inches squared, I almost wrote that wrong. From here, you take that 8.86 inches and multiply it by the thickness of the web. What is the thickness of the web? Which gives us an area of 2.57 inches squared. See why we don't take the area of the total area? Because it's like a quarter of like the area.
I did that approach though. I don't know where wrong.
Yeah. And so from here, you plug in the shear force, which we said was the 25.78 kips. and then divide it by 2.57 inches squared, which gives us a shear stress of around 10.03 KSI. Now, what is the shear strength of the steel? One thing you'll notice is your table doesn't exactly explicitly give it to you on here. So one thing I will allow you guys to do is just write a note on there that the yielding capacity for shear for just structural steel members like W shapes is approximately 60% the yield strength, which you'll see like when you take 36 and multiply it by 0.6, you get 21.6, which they just round down to 21 kips per square inch. If you were to do it for the grade 50, you would get 50 times 0.6, which would just give us a shear strength of 30 KSI, because this value is 50. And hence, because this 30 is greater than the 10.03 KSI, our design is good. Any questions about that? All right. Now, there is one thing now that I'm thinking about it that I want to show you. It's not going to show up on the recording, though, I don't think, but I definitely want to pull it up just so I can show you guys, like, what some of these things look like. I did create this little, like, diagram in Excel. And I'll actually upload it to probably Brightspace, just so you guys can see how the calculations kind of work. Oh, that's the wrong one. Let's see. Jeez, this is taking a million years. All right. Yeah, so I developed a spreadsheet which basically calculates the normal and shear stresses. This first one is just for a rectangular cross-section. As you can see, the shape is a linear stress distribution along the neutral axis. It's just a rectangular shape. And then this is how the shear stress distribution looks when you use that VQ over IB equation. So the shear stress plot, the normal stress plot, uses the equation sigma is equal to my over I. We're just, now the value y is just this y-axis here. And then the x-axis is your stress. All right? But the shear stress, however, is equal to the tau is equal to VQ over IB equation, which then technically Q is, we discussed this, Q is equal to the A tilde times Y tilde, which then technically the A tilde is equal to some function of Y, which I think was like B basically quadratic, which is why you have this like curved look to the shear force diagram. So it's like a quadratic thing. Now, for W shapes, however, the W shapes are a much more complicated calculation, which, yeah, this used up 141 cells of repetitive calculations. And these values just show you what the plots kind of look like. So if you guys want, this is interactive. I could upload it, but for example, like if I change one value, this diagrams kind of change. So I could change that to now be 1 inch, which then the shear stress distribution looks more like that. 5. You can make this like 0.5. You can make this like 2. And so you get these weird shear stress distributions because the neutral axis just really varies. So if you guys want, I can upload it to Brightspace just so you guys can kind of see how the calculations work. But if I were to show you guys like average web shear, for example, what was the area? Here, let's actually try it. What was the width of the bottom flange, of the top flange for the W10 by 33? What was it? 7.96, yeah. And that's going to be the same for the bottom flange too. What was the thickness of the web? 0.29. And then the thickness of the flanges?
0.435.
And then the height of the web?
435.
435. And then the total depth of the beam? 9.73.
Yes.
Which that's how the shear stress distribution would look in terms of PSI. Is that right? Oh, the bending moment. What was the design bending moment that we got? It was 1687.5, but you got to multiply it by 1,000 because I have it expressed in units of pound inches. The shear stress was 17.1875. And again, multiply it by 1,000 because you've got it in terms of pounds. And as you can see here, what was the area now? So I'm just going to add this web shear approach. I'm like adding a bunch of like random spaces here. Interesting. There we go. We said that the area of this web was equal to this times this, which is inches squared, which means shear for this would have been equal to that divided by this, which I'm just going to plot this really quickly. So select data point, add series. I want this value to just be 0. And then this value, or not. And then this value here just to be that. As it proceeds not to plot it. Thanks. Hold on. I promise there's a reason I'm doing this. Just bear with me. Change chart type, combo plot. Why is it doing that? There. And then I want this to be a scatter. Oh. Or do I not want that? I don't know what this thing is doing, but where'd it go? Here we go. Here. You guys can kind of see, probably not. Let me make this larger. There's a reason I'm doing this, I promise. 5. Or not. Come on. I'll just zoom in. Do you guys see the plot? Using the VQ over IB equation, you would get that the shear stress is whatever the maximum blue value is. But the red dot is using the average web shear approach, which is that just accounting for the shear stress from the web. So, knowing this, which would you guys prefer? VQ over IB and do a ton of calculations, or average web shear approach? Average web shear. Now, you cannot use average web shear approach for a rectangular shape. So that would be this. Because if you were to take the area here, and we set the area is just going to be B times H, which is just going to be inches squared, which means that the shear stress is just equal to this divided by, the shear stress is just going to equal the shear force divided by this, which is going to give us units of PSI. Did I write the correct units here? Yeah, I did. And so now if we tried plotting this on this plot here, whoops. You guys can kind of already see where we go wrong. Is using the average shear stress conservative in this case? No. This is following the VQ over IB, which gives us the maximum shear stress over here. But if you just use V over A, you get a significantly reduced shear stress. Does that make sense? Now there's a good rule of thumb. For rectangular cross sections, the maximum shear stress, I believe, is equal to 3 over 2 tau average, which is just the 3 over 2 times V over A equation. So if you guys ever have a rectangular cross section and I ask you guys find the maximum shear stress, you guys can just speed up the process by using this equation. Unless you guys just want to use the VQ over IB. This is not always the case. It is only for rectangular sections. This is not for W shapes. The cross section can only be a rectangle with dimensions B and H. Okay? Are there any questions about anything that I just showed? Did I just? Oh. So, what did we learn? Basically, let me just come back here. I will upload the, oh, whoops, come on. Why is this off now? Yeah, here we go. So basically, we get that for rectangular shapes. Tau max is approximately 3 over 2 tau average, which is just your V over A equation. And then for W shapes, tau max is approximately the shear force divided by the area of the web. I'll just draw a little diagram here. This is B, this is H, and then this whole thing here is AG. And then the area of the web here is just this area bounded in here. Where this here, this dimension, is dV. And dV is just equal to d minus 2 TF. I don't plan on giving you guys any more complicated problems because in practice, we don't generally deal with circular shapes, right? The two most common examples that you can think of. A rectangle. What structural elements are rectangular? Wood elements, right? Wood beams. You ever see a circular wood beam? I mean, they exist, but they're not common. All right? You guys ever see a triangular wood beam? No. So, yeah. And then obviously for W shapes, they look like that. Any questions before we go to break? All right, let's come back at like 7:15. In the meantime, I will come up with another example. Hey, Joe. Oh, wait. Oh, that's interesting. Mohr circle is in this textbook. I did not know that. Now I do. I thought Mohr circle was only an engineering topic, but it is literally right here. And this is a textbook for you guys. Where'd my pen go? This problem's now a composite problem for beams, for flexure only. Which we did cover a composite problem previously. It just involves transforming one of the sections. Don't make it redwood. Don't make it red oak, I mean. I want this to be... Let me just check some stuff really quick. I want this to be shagbark hickory, and then this I want to be western hemlock.
Shagbark.
Yep. And yes, shagbark is a genuine wood, apparently. It's in your packets. And I want you to find the max normal stress, or bending stress, I should say. And then I'll give you guys about 15 minutes to do this. We did an example of composites last class. It's just following a very similar procedure. I think we did it last class. I'll need to double check. Let me see. That we did. Composite beams. Yeah.
Can I get some assistance?
No.
We'll make more.
Well,
I don't remember from watching the so.
oh, you just said never mind.
No, I said I don't remember the lecture. It's,
Yeah. Basically, what you need to recall is how to develop the tables. All right. So step one was determining composites or any shape that isn't a standardized shape are section properties. These are like your A, your Y bar, your IX. So you need to determine that. That's just your statics. The trick with this though is that you have two different materials now with two different moduli of elasticity. So what you need to do is, for composites, transform the materials. And the way that this is done is by just multiplying the area by what? Modular ratio. You guys remember that? What? Exactly. All right, just keep in mind which material you're transferring to what. Generally, I would take the stiffer material. In this case, I believe it's the shag-bark hickory, and you would multiply that by n, because then the dimensions will be increased, which in turn would increase the split. But it doesn't really matter too much, like you don't need to sketch it out. All I would do is just take the thicker element, take the high number divided by the low number, and then multiply the area of the shag bark by n. You could do it the other way around too, but yeah. And like I said, or I think last class, in an exam setting, I'm not going to ask you guys to do a full-fledged problem like this. Like, it's very involved. I may ask you guys, find me the second moment area of inertia with it transformed to shag bark hickory, which in this case is just part one of this problem. Or I may ask you, I may give you like the transformed section properties and then ask you, find me the stresses. In which case then you'll need to know how to calculate the stresses and what material to apply n to. And that would be like another type of problem I could give you on the exam, which is part two for this.
Could you show us, like, clearly which one is being transformed?
I will explicitly state which material is being transformed or not. Because obviously if I give you a bunch of section properties and you don't know what material it is, you can't solve it without knowing. It would just be way too complicated. I'll be right back. And in case you're wondering what type of structural element might be just wood and shaped like this, here's something I grabbed from Professor Simon's class. You guys have seen stuff in this classroom before, right? Something like this, just with some type of load on it. I might make that an exam problem. Just bring in 2 tables, span something across and tell you guys this, check it. I'll put some arbitrary weight or tell you guys to figure out what the weight is. I think I'll just leave this here just so that way it aggravates somebody. The next person who teaches it. Professor Neiman. She'll be like, why the hell is this in here?
They were looking for something this Monday too. Something was missing from his classroom, and Professor Neiman, Professor Simon were looking for it. I don't know what it was though. Now they're gonna look for that.
No, I'll put this back before I leave. Did you guys figure it out yet? Yes. Sure. This and this? Yeah.
Well, that and then the
Well, you want all of these just to be one material. Because you want your IX to account for the varying stiffnesses of different materials. So, because of that, you can do one of 2 things. You can either do the checks to transform this, or you can do the checks to transform this. Should we just work on it together? Okay.
See how it's done.
All right. So, did you guys at least calculate what the modular ratio needed to be? And what did you get?
It's just 1.375.
Ye. It's unitless. Because you're taking kips per square inch divided by kips per square inch, so your modular ratio is always unitless. All right, then from there, we want to determine the section properties. So this is just going to be our components tab. We need an area tab, a Y-bar tab.
Screen is frozen.
Of course it is. Unfreeze and unfreeze. So I've got a component, A, Y-bar, an A Y-bar, and then once we determine that, we've got a dy, an ADY squared, and then a separate IX. All right. However, there's one thing that's nice about this problem. Where's y bar? Did you guys figure that out? What do you guys notice about the shape? Symmetric. Where's y bar then? It's at the center. So you could just say y bar is equal, I'll actually just write that here. Y bar is equal to, let's see. That's going to be a ½ inch. So y bar is equal to ½ an inch, because that's this dimension here, plus 4 inches. So it's just going to be 4.5 inches. One thing we still need, though, is the areas. So let's get the top flange. We've got the bottom flange. I'll actually do top, web, and bottom. And the bottom flange. Areas of the top flange. It's going to be 4 times 0.5, which is just going to be 2. The area of the web is 8 times 0.25, so that's just 2. And the area of the bottom flange is just 2. However, we want all of this to account for the material variation. What did I say about multiplying the modular ratio by the area, right? So what we want to do is we want to transform this. So we take that 2 for the top and bottom flanges and multiply it by the modular ratio n, which then is just going to be 2 times 1.375, which gives us an adjusted area of 2.75. And what this does is, instead of it being the red and blue as we see up here, I'll show you guys in a second. What this does is it transforms, and when I mean transform, I mean it literally creates an equivalent section giving equivalent properties. And this isn't like paste. Oh my goodness. I'm losing my mind. You know what? I wish I knew how to... Oh, wait. I wish I knew how to paste text on here. Sometimes I can do it, sometimes I don't. So you guys will just have to deal with me drawing it really slowly. So sorry about that. So that's flange 1, web, and then flange 2. And what this does is it basically takes the flanges here and basically gives it an updated area. So if this is the red flanges here, and then this is blue here, guess what? By multiplying the red by n, then we get equivalent dimensions or equivalent areas here where this entire cross section is just now blue. Does that make sense? So the area of these flanges now is just 2.75. And that's what we're ultimately doing, is we're accounting for the stiffnesses by replacing them by an equivalent area that would cause the same amount of same behavior. From here, we need dy. Where is the location of this with respect to the neutral axis? Well, it's just going to be 4.25 inches. Does everyone see where I get that? 8 inches is the height of the web, divided by 2 gives you 4. And then you need to add half the flange thickness because we're trying to find the center of the flanges, which gives you 4.25 inches. Does that make sense? All right. So this becomes 4.25 inches. Where's the web with respect to the neutral axis? How far away is it?
0.
Yeah, because it's at the neutral axis. So that's 0 and 4.25 inches. And so from here, we just take the area and multiply it by ADY squared, or multiply it by dy squared. So 2.75 times 4.25 squared gives us 49.67. That's going to be 0, and then 49.67. And then because these are all rectangular shapes, we use BH cubed divided by 12 for IX, which is just going to give us the updated properties. So what we need to know is this width here, the updated width. The trick with this is knowing that this is still going to remain as ½ an inch, which means that this is technically the width times n. So the width of the flange was initially 4 inches. So it's 4 inches times 1.375, which gives us 4 times 1.375, a width of 5.5 inches. And so this becomes 5.5 times h cubed, h being ½ an inch, divided by 12, which gives us some really small number, 0.0573. This becomes a quarter of an inch multiplied by the 8 inches cubed divided by 12, which gives us 10.67, and then this is just the same. And so you sum this whole thing together, you get 99.34 on the left, and then 10.78 on the right. And so your IX total becomes 110.12 inches to the fourth. Does everyone follow along with this? It's basically just statics. The only thing you're doing now is just multiplying certain things by the modular ratio just to transform things. Any questions about this at all? About this procedure, what we did, why we did it? Yeah.
How do you know when to multiply by n?
Depends on what material you're transforming to. So
So if you have more than one material, you're always going to multiply by the modular ratio?
yes. Now it's just a matter of knowing what material you're transforming to. In this case, you are taking the stiffer material up on the top and then the less stiff material on the bottom, which means you are transferring from stiff to less stiff. So whatever's on the bottom is always what you're transforming to. Now, if we wanted to find the equivalent second moment area of inertia that would transform everything to the shagbark hickory, then you would just transform everything the opposite direction, right? Which conveniently is just going to be the 110.12 divided by the 1.375. And that's because now you're transforming this entire cross section to everything red. So this is for shagbark, and then this is for western hemlock. But ultimately, the stresses that you calculate will be the same no matter what. It's just a matter of knowing how to manipulate the values. Any questions about this? Are these the true second moment areas of inertia? No. In reality, it's like you can technically have two. It's just like just a matter of playing with the numbers a bit. So, how do we calculate the stresses now? What we need to do is use our sigma is equal to my over I equation. This is a symmetric shape, so you could technically, I guess, say you wanted to do m over s, but I wouldn't necessarily do that. Just avoid this step. It's less confusing. So now we want to find the stress in the western hemlock. So what we would get is my over I, which let's say we didn't know this shagbark second moment area of inertia. What we would do is just the 1 kip feet times the y bar, which the y is the location or the bounds at which the western hemlock goes. How far up does this western hemlock go? It only goes up 4 inches from the neutral axis, right? Because once you pass like this point right here, it's not western hemlock anymore. It's the other wood. So y can't be any greater than the 4 inches. So we just have to multiply that by 4 inches. And then, of course, you want your units to be consistent, so multiply it by 12 inches per foot to get everything in terms of inches. And then your I is going to be the 110.12 inches to the fourth. And what we get is a stress of 0.436 KSI. Now, if we wanted to calculate the stress in the shagbark hickory, we again use my over I. But now the thing is, the shagbark hickory is way above the 4 inches. The max stress in the shagbark hickory is occurring way up here. So you need to do it by multiplying it by 4.5 inches. And then divide it by I, which is 110.12 inches to the fourth. But now, because we are in the shagbark hickory, you need to multiply it by n, which is the 1.375. I guess another way you could do it, what did we say was the total IX for the shagbark hickory again? What was it? Did somebody write that down? All right, 80.9, 0.09? So You could do it that way, or you could just take the 1 kip feet, multiply it by the 4.5 inches, 12 inches per foot. And then just divide this directly by the 80.09. Either way, both answers will give you a stress of around 2.67 KSI. And you can feel free to fact check me on that. So that's really 2 methods of just being able to do it. Any questions about this at all? All right. Now, if I asked you guys to plot how the stresses look or vary along the height, basically, the stress distribution would just look kind of like this. You would have a positive bending stress here. It would be somewhat linear downwards. Then it would significantly drop to about here. Then linearly decrease across the neutral axis. Re-increase over here. Immediate jump again. And boom. So this value here is that 0.436, and then this value way up here is that 2.67. Any questions about that at all? Do you guys think you'd be able to do this on an exam with practice? All right. Let's do another example now. Let's say now instead, I give you guys a T shape, just like that. And now this in the red, I'm going to say is A36 steel. And then this blue here is aluminum. Alloy 1100 H14. I'll say that this is about a 1/2 inch by 6 inch plate. And then I want to say that this is also a 1/2 inch by 6 inch plate. Yeah. So what I want you guys to do is find the second moment area of inertia as both A36 steel and as the aluminum. I'll give you guys about 10 minutes to do that. Think you could get it done in 10 minutes? We just did an example just like it.
Proposal for the stresses.
Yes, if you have the second momentary of inertia, I will say. You have the second momentaries of inertia already?
IMX.
Yeah,
Yeah.
you do?
If it's working.
All right. Anyone else have IX? Somebody else does. All right, sweet. I'll just wait a few minutes just to see who else can finish up. All right. Most people should have an answer. Let's go over it. All right. So, what we first need is a components table. We need an A for in units of inches squared. We need a Y bar, which is going to be in units of inches, and then an A Y bar, which is going to be in units of inches cubed. All right, we've got the flange and the web. Area of the flange. So, Michael, how did you do it? Did you transform it to steel? Did you transform the...
Steel.
You transformed the steel to aluminum?
I multiplied N by the steel. I
And-
multiplied the steel by N. Excuse me.
Okay, how did you do it, Olivia?
I transformed the aluminum into steel.
Aluminum into steel? All right, so what did you get for the modular ratio?
I got 2.87.
And what did you get for the modular ratio?
2.87.
2.87. So you transformed the aluminum to steel, and you transformed the steel to aluminum. And you both had the same modular ratio. One of you is right, and the other one is way wrong. Who's right? Olivia's right? Let's see. So the modular ratio is equal to whatever we are interested in. So this is the current material to transformed. So we want to transform. You said we wanted to transform. How do you guys want to do it? How would you do it? You said aluminum to steel, you did?
I just did the stiff material on top. That's what you did.
You did the stiff material on top.
Yeah, I can see.
29,000 KSI over the 10,100 KSI. Raise your hand if you think this is transforming steel to aluminum. Raise your hand if you think this is transforming aluminum to steel. Raise your hand if you decided not to raise your hand. 1, 2, 3, 4. All right, 5. Great. So nobody has an opinion. All right. So I'm going to ask this again, explicitly for the 5 students who didn't raise their hand. Who here thinks this is transforming the steel to the aluminum? Aluminum to steel. Is everyone in agreement that it's transforming aluminum to steel, basically? All right, you're wrong. It's steel to aluminum. The reason being is because the steel, you need... Hold on a minute. Let me figure this out now. Yes, you need more aluminum to equal the stiffness of the steel. So because of that, when you transform the steel, your section is going to get larger even though the stiffness is smaller to compensate. So because of that, this is transforming steel to aluminum. 29,000 divided by 10,100 gives us the 2.87. We both agreed that that's the modular ratio. I think there was just a mishap with the definition. But basically, what this means is the steel is equivalent to about this much area of aluminum. So this is just going to be, the area is basically just going to be 1/2 times 6 times 2.87, and that's the equivalent area for the aluminum. I'm sad that everyone was wrong in this except for Michael, and Michael even doubted himself. So he's even technically wrong, even though he was right. So really, this adjusted width here becomes 6 inches times 2.87, which gives us 17.23 inches. And then the height is still a 1/2 inch. And then this, of course, is still a 1/2 inch by 6 inch plate. So the area of the flange just becomes the 17.23 times the 1/2 inch, which is equal to the 8.614 inches squared. Does everyone see what I did and why we're doing that? Yes.
I'm just a little confused.
Okay.
So, I thought you were
The modular ratio relates the stiffnesses of one material to another. The material that we are transforming into is always on the denominator, I said this earlier. So, if we want to transform the steel to aluminum, the stiffer material goes on the top. Think of it this way. You need this much aluminum to equal this much steel. Otherwise, if you're increasing the area of steel, then you're just significantly increasing the stiffness. You're trying to find an equivalent material to match the stiffness. The way you kind of did it was you just increased the stiffness of the steel, which in turn basically makes the aluminum worthless.
I did what?
You basically multiplied this. You transformed the aluminum, right? Which then increased the size of the aluminum, which is then saying that steel is technically stiffer than aluminum. Does that make sense? Or that aluminum is stiffer than steel. It's confusing, but just be careful with how you apply it. Basically, always transform stiffer material to less stiff material. So the aluminum is less stiff, so because of that, transform the steel. So that gives us an area of 8.614 square inches. For the web, we are still at 3 inches squared because it's 6 times 0.5. Next, we need Y bar. Because this is not symmetric, we got to calculate this individually. The Y bar for the web is going to be 3 inches from the base. And then the Y bar for the flange is going to be the 6 plus half the half inch. So it's going to be 6.25 inches. Lastly, just carry it over. 53.84, 9. And then you just do the math. Just give me a minute. We get 25.84. 2 here, and then plus 9, we get 62.837 here, so that means our total Y bar is roughly 2.432 inches. Is that what you got initially, Michael?
You get 25.8.
I multiplied it by accident. 8, 9, 10, 11. First mistake of the semester. So 62.837 divided by 11.614. That makes more sense. A Y bar of 5.41 inches.
Yeah, that's what I got.
That's what you got. Good. Now from there, we need to calculate dy in inches, ADY squared in inches to the fourth, and then IX in inches to the fourth also. dy is just going to be the Y bar total minus the Y bar of each component. You could think of this as the total Y bar. And so we get, for the first one, 0.84 inches. And then for the second one, we get 2.41. 3 times 2.41 squared gives us 17.42. And then 8.614 times 6.25 squared gives us 336.48. And then for IX, again, we're dealing with rectangular shapes, so use BH cubed over 12, which for the web is going to be the half times 6 cubed divided by 12, which is 9. And then the IX for the flange is going to be the 17.23 times the 1/2 cubed divided by 12. Which is just going to give us 0.18. Lastly, just add all of your numbers together. For this one, we get 353.9 and then 9.18, which means our total IX is equal to 363.08 inches to the fourth. And this is in terms of the aluminum. Is that what you got? Now, if we wanted it in terms of the steel, take that value and divide it by that 2.87. And that gives us the 126.51 inches to the fourth in steel. Yes?
How did you get Y bar again?
The Y bar is taken as the sum of a Y bar divided by the sum of the areas. So this would be that sum of a Y bar. And then this is just the sum of the areas. And so it's just the 62.837 divided by the 11.614. Are there any questions about this?
And to get the steel, you divided it
By the modular ratio, yes. Which then you can use in calculation to determine the stresses. Is this an actual second moment area of inertia? Not really. It's just a hypothetical that we're using for mathematical purposes. Because again, it's just a section property for a given material, so there's not really one true section of material property or cross-sectional property for it. It just depends on what your given material is. All right, time for your get out of jails. I'm kidding. I'm not an evil human being, I promise. Just some last minute announcements. I moved back your homework 9 because that is pertaining to deflections, which is not being put on your exam. So that is now due after break, in case you guys see it. And there is no homework due next week, that means. So, enjoy your weekends. Please study so that way you guys can do good on the next week.